So, if you want to see how yesterday's class played out, I actually had that uploaded yesterday. If you go to YouTube, if you want to watch yesterday's lesson, all that good stuff. So, day 2, physics students. So now we're actually going to kind of get into the heart and soul of this thing. We end up doing a lab with springs and all this good stuff. And so, and then let me explain. It's odd that in 52 years on this earth, I've never worn a bracelet. Okay, so it's a little bit weird for me. So don't look at that and go, well, here's a guy that wears a shirt, you know, a tie, and he's wearing kind of this like earthly kind of bracelet. It's a long story, but my brother and his wife ended up taking in 2 students from Nigeria that were over here going to Cape and Mount Carmel, and they needed a place to stay. And so anyway, so it was brother and sister, and so they stayed with my brother and his wife. And so I became known as the uncle because of my relationship with my brother. And so they went back to Nigeria over the summer, and they came back and they brought, you know, some, you know, gifts for everybody, and they brought me this, and they said, you know, you have to wear this when you're teaching. And I was like, okay, because, you know, in Africa, someone gives you a gift, it's important. And so I've never worn one, so don't look at this and go, wow, Burkham has like Birkenstocks. Where's the bracelet? No, okay. Huh?
What's wrong with Birkenstock?
It's just not my style. Okay, I was even in the Peace Corps for 2.5 years. Okay, this is how sheltered my life is, okay, growing up. I never even knew a vegetarian until I joined the Peace Corps. Or a Democrat. Or people that wear Birkenstocks. They're all the same. But I know that's stereotypical, but go with it. Okay, it is, it's stereotypical, but I can be that way. So, it's just been my experience. So, okay, so let's talk physics. So yesterday we kind of laid out, hey, this is what physics is. And as we go through these equations and everything, and how we're going to, the units that we're going to use, here's the overriding theme that you have to keep in mind. Physicists use math to describe a situation. Okay, that's the nuts and bolts of it. So, has anybody here ever read anything by the author Ernest Hemingway? If you've never read anything by Hemingway, do so. Like he's written some great short stories like The Snows of Kilimanjaro. So Hemingway spent a lot of time in Africa, and so when I read Hemingway, he does such a good job of using words to describe the essence of Africa that I can read that and go, wow, you know, in my mind, I'm back there because he does such a great job of using words to describe a situation. Physicists have to use math to describe that situation. So, you know, if I take this apple and I drop it, okay, great, it's gravity, cool. So if I'm a writer, I can go, oh, parting of the hand from the apple was such sweet sorrow, and it left, and it began to gain, you know, so we can use flowery words to describe what's happening, but, you know, and then it quickly stopped, and it hit my hand, and all this good stuff, okay? But God talking like that just makes me want to wear Birkenstocks. Anyway, so, maybe it's the bracelet. Anyway, so, but the problem is we need some numbers, okay? We got to have some numbers to put into it. So at the end of the day, if you're a writer, you use words to describe what's happening in a situation. If you're an artist, you use clay or wire or charcoal or whatever that you use. Physicists use mathematics. And so this is why, basically, if you study physics, you've got to do a tremendous amount of math because it's basically math applied to a physical situation. So that's kind of the heart and soul of this. So that's the whole thing that we're going to do throughout this entire course. Is say, okay, here's a situation, plane takes off an aircraft carrier, an apple falls from a tree, a freshman gets launched out of a cannon, whatever the situation is. We use that example. And so then, okay, how far is the freshman going to travel? You know, stuff like that. So that's what we're trying to figure out. And if we can do the calculations and we say, hey, the freshman's going to travel 35 meters, and we actually shoot the freshman and he travels 35 meters, hey, cool, okay? Now, if the freshman actually travels 70 meters, ooh, something went wrong. Our bad, you know? So he was supposed to hit the target where the landing spot was, and he overshot it. I don't know what happened. Okay, so on the notes that I gave you yesterday, there's 3 fundamental things that we're going to use in physics. And hopefully this board works first, the reason that there's a whole bunch of writing over there on that board is because the first block, my spark board, was being stupid. So hopefully, I talked to it, and hopefully things are going to work out better. So far, so good. Now, so one of the things that you've got to begin to figure out is the difference between the units that we use to represent things and the variables that we use in an equation, okay? They're two completely different things. They're related, but they're two completely different things. So, to talk about meters, there's any number of things that you can measure meters. Like today in the lab, what you're going to do in the lab is that we're going to measure how far you're going to stretch a spring. Okay, pretty simple. You're here, boom, how far is it going to stretch? Sometimes we measure exceptionally small distances, like, okay, what's the diameter of a hydrogen atom? Okay, that's a pretty small number. Versus, hey, what's the diameter of the Milky Way galaxy? Okay, that's a pretty big number. Okay, so with physics, you go from extremes. Okay, you might have something like 10 to the negative 13th if you're an if you're working with particle physics, but if you're on the astronomy side of physics, you might be working with numbers like 10 to the positive 13th. So physics has this big range of things. But no matter what, everybody works off this idea of meters. It might be a very, very small number of meters. It might be an extremely large number of meters. But everybody's going to work off this concept of meters. Okay, you won't struggle with that one. So typically, when you see something as a variable, an x, a d, or an L in an equation, that means that you're going to be talking about something that you're going to measure in terms of length. Okay? So like one of the equations that we'll use is distance equals 1/2 at squared. So when you see this distance, hey, how far is this thing going to travel? Here's your acceleration, here's your time. If you're talking about a pendulum, you might see the period of the pendulum is 2 pi times the square root of L over G. Okay, in that situation, you're using L to measure the length of that pendulum. So when you see it as a variable, you'll, okay, that's going to be a distance, okay? Distance has more different kind of variables than about anything else in physics, because sometimes it's an L, sometimes it's a D. If you're talking about like the Earth as it orbits around the sun, you're talking about a radius, or like an electron orbiting around a nucleus. So it might be a radius, it might be a diameter, but basically anything like that is going to be measured in meters. Okay, not a big deal there. Seconds, you're going to see that as time. That's not a big deal, okay? Occasionally when we get into planetary motion, like we're going to be talking about like the orbital period of Mars, okay? That might be measured in years, okay? Just because of the sheer numbers. You know, it's like the classic example. Why don't you measure their, why don't people express their age in seconds? Why don't we use seconds for our age?
It's an insane number of seconds.
It's an insane number, okay, especially as you approach my age, okay? What else?
We have large measurements.
Oh, it's easier to get, yeah, just remember years, okay? But the problem with seconds is it's continuously changing. It's like, how old are you? 5,300, oh God, it already changed, okay? Because if you're trying to express it in seconds, literally by the time you say how old you are in seconds, that number is passed, all right? And it's just not convenient, so that's why we use years. Okay, all right, there we go. Now, kilograms is what's going to give you more fits than anything, okay? You mark my words, kilograms is going to give you trouble. So we're going to spend some time going over this so that you say, okay, here's the potential pitfall. So kilograms is a measure of mass, so we use the variable m. So this is where the first sense of confusion comes from. You see m and you think, oh, that's meters. Okay, so let me give you the classic example. So on that sign back behind you, you've got this big thing that says F equals ma, right? F equals ma. We'll talk about this equation today because it's going to be the basis of the lab. So this is force, this is mass, this is acceleration. So when you see an m as a variable in an equation, that's going to be mass. If we wanted meters, we would have like an x, a d, or an L, or something like that. So when you see M as a variable, that's going to be mass that's in kilograms, okay? So don't confuse those two. Now, you sit here and go, oh, Mr. Burkamp, we won't do that. You lie. Trust me. There has not been a single physics class that I've ever taught where somebody doesn't see this as M and leave it as meters, okay? It's going to happen. I've accepted it, okay? I've moved on, you know, we're not good with it. One time I'd love for a class to prove me wrong. It hasn't happened yet. Hopefully this time. So that's a potential source of conflict. Now, the other thing is y'all aren't used to thinking in terms of kilograms. Length, you're okay. Time, seconds, you got that concept down. So here I've got a 1 kilogram mass. If you spend a lot of time in the weight room like I do, okay, I lied about that. I don't. In case you can't tell. But that wasn't that fun. Don't make me flex. Oh! Okay. So, what? I would, I'd rip my shirt. Don't make me get big. Okay. Everybody laughs when I say that. One time there's two things that always people laugh at when I say I lift weights, and they go, whatever. Okay. And then I say, oh yeah, that's why I make the big money as a physics teacher. And kids always laugh at that too. It's like, you don't get paid any more than anybody else. Like, I know, but it sounds good. Okay, so, yeah, me and the PE department. Okay, so here I've got a 2.2, this is 1 kilogram, which is about 2.2 pounds. Okay, it's about the equivalent thing. So everybody confuses mass and weight. Okay. In a physics perspective, they are two vastly different things. They're related, but they're vastly different. So this 1 kilogram mass, if I take it to the moon, is still going to be a 1 kilogram mass. Okay? Mass is a measure of how much stuff there is inside. So as long as I don't change the amount of stuff that's inside the container, I'm not changing its mass. So no matter where I am in the universe, this isn't going to change. Okay, it's 1 kilogram mass. Here I've got half a kilogram mass. Okay, boom, there you go. Right? It's not going to change either. Where weight becomes a factor is, number one, you all are used to thinking as weight expressed in pounds. Okay, what do you weigh? Oh, I weigh 150 pounds. Okay, in a physics setting, weight means something different. Weight is reflective of a force, meaning that you're going to have an interactive situation with a gravitational field. So if I have 1 kilogram mass on Earth, and you'll see where this number comes later, it weighs 9.8 newtons. Okay, that's a measure of the gravitational attraction between this and this big rock that we're on. Okay, if I take this thing to the moon, it's going to weigh less because there's less stuff on the moon to interact with this. Okay, so weight changes, mass doesn't. Okay, so that's the first thing I want you to understand. So when I talk about weight in a physics class, I'm talking about an interaction with a gravitational field that will change depending upon where you are. If I'm talking about mass, I'm talking about a fixed value that is not going to change based upon where you are in the universe. Okay, so weight, mass, related, but not the same. Got that? Okay, so in physics, these are basically, you can think of this as being the letters of the alphabet. Okay? So when you all were little, you were taught the ABCs. ABC, okay, and you thought you all were cool. It's like, wow, you know, Skippy learned his ABCs. So cool, okay? You can count to 10. Mom and Dad probably posted on Facebook because it was such a monumental event. Physics, alphabets is easy. Okay? We have the MKS system. We have 3 letters. Now, just like you can take the letters in the alphabet and form words like supercalifragilisticexpialidocious, okay? You can arrange those letters and you make something different words. We can arrange these into into other things as well. But here's the beauty of this. This is why physics is so sequential and it's so logical. These are the only 3 units we are going to work with between now and the end of this class. We're going to put them in different combinations to get like momentum and energy and that type of thing. But literally everything that you are going to express between now and the end of this class is only going to be some variation on these 3. That's it. Nothing else. Okay? That's it. It's a home run deal. All right. So we got this. So the first thing we're going to do is we're going to combine these into velocity, okay? So velocity, and there's a whole bunch of different ways you can calculate velocity. There are probably, off the top of my head, I can probably name you 10 different ways to calculate velocity. The simplest way to calculate velocity is that some distance divided by time, okay? So Max is going to go out, and we're going to have Max run, and we're going to have him run like the length of the football field, okay, which is about 100 meters. Okay, so here's Max, okay, right? Woo, runs, okay, runs about 100 meters, and we're going to time that, and let's say that took 20 seconds, okay? So he's going to run 100 meters, and we're going to time him, and that's going to take 20 seconds. What? Actually, no, it's not. No, you'll see, this isn't bad. Okay? And you'll sit there and go, no, actually, when we get done, you'll see why this is a reasonable value, especially over that long a distance. Okay? So, and that's assuming that this isn't a race. Like, he's not being chased by a lion. Okay? Because the lion, I can guarantee you, can make this thing in about probably 10 seconds. If Max takes 20, Max is lunch. Okay? So maybe he's being chased by like a hippo. I don't know. All right. So here's the numbers. Well, I want to figure out how fast Max is running. All right. Well, that's simple. So here's how physicists approach this versus how you do this in a math class. If I gave you this number in a math class, problem in a math class, what are you going to do? I want to know how fast Max is running. What are you going to do?
Divide 100.
Divide what?
100 by 20.
Right? And if you're in a math class, this is what you're going to write down. I swear to God, this is what you're going to write down. You're going to write, if you write down anything at all, okay? If you write down anything at all, you're going to write 100 divided by 20, and then you're going to put that. And in a math class, that will get you full credit. Okay? Because, and this is the fault of the education system. For 12 years of your life, you all have been taught to focus on this number. Did you get the right answer?
No.
Why?
Unit.
Those are 5 meters per second.
But in terms of a numeric value, this is what you focus on, though. Did you get the answer of 5? Yes. Now, but what's missing? Yeah, because if you just say the answer is 5, what do you not know?
5 what?
Yeah, 5 what? Are we talking 5 hippos, 5 meters per second, 5 light years? What is this number? I don't know. I got nothing. Okay? But you're used to focusing on this number. Did I punch the numbers into the calculator? And you all view your calculator as like an oracle, where it like gives you this answer and you feel obligated to write it down. Oh, the oracle has spoken. The answer is 5. I must write it down. Okay? We'll spend on Monday, we'll spend a whole day talking about your relationship with your calculator. So, but if I take the 120 divided by 5, boom, you get 5. Now, but if you put down the units, 100 meters divided by 20 seconds, now I get 5 meters per second. So here's the paradigm shift that you have to make to be successful in this class. You have to get past the idea that Burkamp is worried about the answer, okay? Yeah, don't think I'm not, okay? I am. But that's like the end product. I am just as concerned, or if not more concerned, about the process that leads you to that answer. Because like in this lab that you're going to do, you're going to have to find slope, you're going to have to do some calculations, and if all I see is the answer, and just the product, without the process that got me to that point, I don't care. I literally do not care. Because if all I was worried about is the answer, I wouldn't leave all this space. I wouldn't give through this whole process of showing you, hey, this is how you do a physics problem. So the sooner that you embrace this idea that, hey, I'm going to focus on the process and not the product, you're going to become more and more successful in this class. So you have to get out of this mindset that, oh, I got the answer, who cares how I got it? That's not the point. And that's not the point in life, okay? Trust me on this one. Here's a little physics philosophy 101, okay? If you focus on the process, the product will take care of itself. But if you're going to try and take shortcuts in life to get just the end result, it is going to be a train wreck, okay? It is not going to work in the long haul. You pay attention to the little things in life, the big things will take care of itself, okay? Trust me on this one. Almost 52 years on this earth. One of the most important things that I can stress to you is that you pay attention to the little things. If you're successful with those, the big things will take care of itself. You take care of the process in physics class, the answer will take care of itself. Because if this part goes south, everything else is going to go south. Now, you all said Max was running slow, okay? 5 meters per second, and you all kind of shuffled. So, Usain Bolt, world-class sprinter, won any number of gold medals in the Olympics. He runs the 100-meter dash in a little under 10 seconds. Okay? Keep in mind he's a world-class sprinter. Okay? So Usain Bolt will run at about 10 meters per second. So one of the things that we're going to do is that eventually we're going to go out in the hallway and we'll have Max run. Okay? Well, everybody remember, Max is going to run when we go out in the hall. Okay? And we're going to have Max run at a full sprint for 10 meters. Okay? Not even starting from rest. You're going to run at a full speed for 10 meters. Historically, that's going to be around 7 meters per second. So, us mortal human beings at a full sprint will typically run about 7 meters per second. So, at 5 meters per second, that isn't that slow. Now, if it took Max 200 seconds, okay, admittedly, we could laugh. All right? But that speed really isn't all that bad over that long a distance. Okay? Cool with this. Now, the other thing that you have to understand about this, and it's subtle, if you haven't ever thought about it. This is actually a rate function, okay? And we're going to spend a lot of time talking about rate functions, how things change as a value of time. It could be a rate of change in momentum as a function of time, a rate of change in velocity as a function of time, a rate of change in position. So what we're saying is that for every second that goes by, his position is going to change 5 meters, okay? That's all that number means. I don't know necessarily which direction he's going. I just know that his position is going to change 5 meters for every second that goes by. Cool with this? We're good. Okay. Now, the other thing is that I'm not a bad teacher of physics, but I can't draw. So now we're going to talk about a car. So what I typically draw in class is what's called the carrot car. Okay? So don't sit there and go, that's not a very good car. For the love of God, I teach physics. It's carrot car. Go with it. Okay. So when you talk about acceleration, which is going to be the next thing. So acceleration, and again, I'm going to begin to get this out of your minds right now. If I say a car is going to accelerate, all I'm meaning is that it's going to speed up, slow down, or change direction. That's it. Okay? So don't think if I'm talking about acceleration, it always means that it's speeding up. It just means that something is changing. Okay? So get that out of your minds right now. So let's say here's the carrot car, right? And I'm going to put V naught equals 0. So let me explain, anytime you see something with a naught on it, okay, whether it's V naught, whether it's like position, whether it's momentum, any variable that has like this 0 beside it means that's the original. This is what we're going to start on. Okay, so that's the easiest way to remember this, is that anytime you see a naught, that means that's the original value. And then I want to change it. So what I'm saying, so when you see V naught equals 0, I'm telling you that the car is going to start off at rest. Okay? So we press down on the gas pedal, we accelerate, and we get up to, let's say, 10 meters per second. Okay? So at this point, you're running about as fast as a world-class sprinter. Okay? And let's say that Grandma is driving. Okay, right? So Grandma's not real, comfortable behind the wheel, right? So let's say that took a certain amount of time, and that took 2 seconds. Okay. So in other words, Grandma presses down on the gas pedal, the car is at rest. Car begins to speed up. Okay, and we're measuring time. You're sitting in the car with Grandma because Grandma's going, "What'd you learn in physics?" And you go, "Wow, Grandma, I learned," or Nana, or whatever you call her, right? It's like, "I learned about acceleration." You go, "Well, let's measure our acceleration." Because Grandma used to teach physics, so her car has a speedometer that measures in meters per second. So you're sitting beside her and you go, "Okay, when I hit 10 meters per second, I want you to stop the stopwatch." "Okay, Grandma, got this." Boom. She presses down on the gas pedal, goes up, she goes, "Oh, I'm at 10, and you look down at the stopwatch, boom, you're going 2, and that took 2 seconds. Okay, so we went from 0 to 10, so something changed, right? We sped up, something has changed at this point. So there's a whole bunch of different ways to calculate acceleration. Here's the simplest one, and this is the one that's most common. Because acceleration equals v minus v naught over time, okay? Now, when you see v minus v naught, this, what do you think, how is this v different from that v?
That's the V you get at the end.
Yeah, this is my final, right? And this is my initial. And no matter what kind of change you're looking at, position, momentum, doesn't make any difference. It's always something minus something not. This sequence never changes, okay? You will never see V naught minus something, okay? It's always going to be something minus V naught, always, okay? No variations on the thing. So in this situation, I'm going to take, my final velocity was 10 meters per second minus 0, and that took all of 2 seconds. Now, don't worry about significant digits, as some of you have been exposed to significant digits. That sounded bad, it's like some tropical disease. Were you exposed to significant digits? Yes, but I got a shot. Okay, we're good. So, but we'll spend a whole day talking about significant digits on Monday. Okay, so mathematically, what are you going to get as an answer? 5. Okay, all right, I get 5. Okay, cool. Good answer? No. Train wreck. Why? I don't know what it is. Okay, 5. Bad. Now, I'm going to give you 3 different options that you can end up with units. 3. Count them. 3. So, one option is that you look at this and go, oh man, I had all summer off, but I think in algebra, I got a seconds down here and I got seconds down here. Those cancel out and I get meters. Okay, that's an option. It's an option. The other option is that, well, this is meters per second. So that means that for every second that goes by, my velocity changes 5 meters per second. Okay, so I can just write it, and I won't get Q or anything, and I'm just going to write that as 5 meters per second, which means that for every second that goes by, this is how much my velocity changes. Just like if you have 10 meters per second, every second that goes by, your position changes 10 meters. Every second that goes by, my velocity changes.
Just wanted to give you a reminder, the school store is open for business. So if you are wanting to get anything from your school store, this would be the time to do it.
Okay. So, every second that goes by, this is how much it changes. That's an option. Now, the other option is that you could look at this and go, oh, I'm going to do a little bit of algebra because I've got like a fraction divided by a fraction, and that work might get lucky and say that's 5 meters per second squared. So I got 5 meters per second squared as an option. I got 5 meters per second as an option, and I've also got 5 meters as an option. So, thoughts from the studio audience? Yes?
So let's say we do that.
So let's say.
So let's say we do that on like a homework problem.
Yeah.
And I put 5 meters and he put 5 meters per second squared.
Yeah.
You'll take both of those answers?
No, I'm just saying these are 3 options. I just want to know if are any of them right or any of them wrong.
Oh.
You'll see that only 2 of them are right.
But wouldn't the 5 meters be wrong?
Why?
Because it's not expressing seconds.
Well, the seconds canceled out.
But now it's only expressing a
This
distance.
isn't bad.
Now it's only expressing a distance, not a
You
time.
can't eliminate
10 meters over, if you were right, 10 meters over seconds, and then you multiply that by just 1 over 2 seconds. Those seconds multiply together, so you'd have it second squared. So it's 5 meters per second squared.
Well done, Grasshopper. Okay. So let's delve into what you just said, okay? Well, let's go with your situation, okay? Let's go with your situation. Let's say that I'm grading your assignments, okay? Which I'm going to spend a lot of time doing. And I got 5 meters here, and I got 5 meters per second squared here, right? So if I see both of those answers, and if that's all I see is this and I see this, do you think, bless you,
Thank you.
do you think logically that we, in physics, that we want a quantity, meters and meters per second squared, do we think we want this to be the same thing? In other words, do you think we want acceleration and distance both measured in meters? Why might that create a problem?
Because we could get confused about what we're talking about.
Yeah, if I just see this, and it's like, I don't know, is it acceleration or distance? I don't know, they're both measured in meters. It's confusing, okay? It'd be a train wreck. It's like, wow, I don't know what we got. I got this. I don't know what it is. I don't know if it's acceleration. I don't know if it's distance. So let's eliminate this, or we'll come back to it. Now, let's go with what you said. If you remember back to your days in doing fractions, right? So if you look at this and go, and all I'm going to look at is just the units. And this is a process known as dimensional analysis. And tomorrow we're going to spend the entire day just doing dimensional analysis. So I got meters per second divided by seconds. So instead of dividing by seconds, what else could I do?
Multiply by
Multiply by the
reciprocal.
reciprocal, okay? So the reciprocal of seconds is 1 over seconds, right? So I got meters per second times 1 over seconds. So if I do it this way and flip this over, right, the seconds don't cancel out. I get meters per second squared. Now, here, again, trust me on this one. The most common mistake made when you're calculating acceleration is you look at this and you cancel out the seconds and you write that as 5 meters. It is the most common mistake that is made. And again, you all sit there and go, Mr. Burkamp, we won't do that, whatever, you lie, okay? It's going to happen, even though I tell you not to, okay? But just think this through. If I take meters per second and divide it by seconds, I'm trying to find an acceleration. It's a rate function. I don't want it to end up in meters. So when you do acceleration calculations, and you'll do a lot of them, I don't care which one of these that you pick. It's up to you. It's a personal preference. Okay? Just pick one. But just don't tell me the acceleration is 5 meters. That's going to be bad. Okay? Go with this. Now, we'll see how you guys do on mental math compared to first block. Okay? We'll see. So let's say, okay, 5 meters per second squared, that's a decent acceleration. To give you some perspective, like if I take an apple or whatever, a freshman, and I drop it, okay? I use freshman a lot. So when I drop this thing, gravity causes a certain acceleration. So the acceleration caused by gravity, and you will see this again and again and again, and we actually call it a specific variable g. Little g is the acceleration caused by a gravitational field. So on Earth, that is 9.80 meters per second squared. You will see this again and again and again and again and again and again. So again, your car, if you like, to give you some perspective, this is a decent acceleration for a car. Typically, most cars can't accelerate this quickly, even if you like really romp down on it. Typical cars might get around 7, 8 meters per second squared, okay? So 5 meters per second squared, you will feel this. Everybody go, oh, grandma, this is a decent acceleration. Grandma, whoever, okay? This isn't bad. Your typical accelerations on a car are around like 2 to 3 meters per second squared. So this is actually kind of hollow in the middle. It's like, grandma, cool, nice. Just hit, all right. Nail it, Nana, here we go, all right. So you can also have like a different acceleration. So let's say that we're going to take a cannon, okay, and we're going to launch a cannonball out of it, because that's what cannons do, right? They accelerate cannonballs. Because if they don't accelerate the cannonball, then there's just really no point in it, okay? So let's say that you have a cannonball, and what do you think the initial velocity of the cannonball is probably going to be?
0.
0. Let's go with that. I think that seems decent, all right? And let's say that when it leaves, let's say that it's traveling at 100 meters per second. Okay, that's about a third the speed of sound, roughly. Okay, this is a decent value. Okay, especially for a cannon. And let's say that that took 0.10 seconds, which is about time it takes to snap your finger. So we lit the fuse, bam, okay? Takes about that long. So did the cannonball accelerate? You should all, at this point, not have any hesitation at all, and you should be saying, well, clearly it did. How do you know what clearly accelerated, Ms. Jones? How do you know that it accelerated? Let me give you a hint. Velocity changed. Did the velocity change? What was the initial velocity of the cannonball? What's the initial cannonball? Is it moving?
No.
It's at rest, right? So we're going to fire up, and it's going to end up at 100, right? So did it speed up? Yeah. Did the velocity change?
Yeah.
So did it accelerate?
Yeah.
Beautiful. Okay? So anytime this happens, in this case it's speeding up, it could be slowing down, it doesn't make any difference. It's going, anytime something changes, that's an acceleration. So we go, oh, okay, well let's calculate that. Okay, well that's simple. We're going to take 100 meters per second minus 0, and we're going to divide that by 0.1 seconds. So, again, without a calculator, okay, this is a little bit of math. If I take 100 and divide that by 0.1, what do I get? First block gave me 3 different answers.
1,000.
Okay? 1,000.
Meters per second.
We'll go ahead and put in meters per second squared. Anybody else have a different answer? Okay, well, first block had 10, okay, and 10,000. So we were kind of all over the board with them. It was first block, they were asleep, they were disrupted because they were calling people out for seeing pictures. But it was like 100? It's like, anyway. So 1,000 meters per second squared. But here's what I want you to begin to differentiate. And that's the difference between acceleration and velocity, okay? Just because something has a slow acceleration doesn't mean it can't go fast, okay? Or just because something has a big acceleration doesn't necessarily mean that it's going to end up going fast, okay? So like when we launch stuff, like say, like Sunday we launched a new satellite that's going to travel and explore the sun. It'll be the closest satellite we've ever sent to the sun, okay? The initial acceleration of that rocket was pretty slow, probably around 2 or 3 meters per second squared. But if you apply that acceleration over a long enough period of time, it can go really, really fast, okay? And again, just because you have a big acceleration doesn't mean that it's going to go at the end very fast. So like for example, in the parking lot, you might push down on your accelerator really hard and then let off on it. So you might have a big acceleration, but that doesn't mean that you're going to end up going very fast if you don't accelerate very long. So we'll talk more about this later. So all I'm trying to do now is plant this idea that just because you have a big acceleration doesn't mean that you go fast. And just because you have a small acceleration doesn't mean that you go slow. Okay? They're two vastly different ideas in terms of how fast you're going and what that acceleration is. Good so far? Okay. Now, we need to tie all this together into one big idea, and that's F equals ma. So this is like the big sign that's hanging in the back. So this is going to be force. Now, here's the question. Is the M mass or acceleration? Tori, is the M mass in meters or is it going to be in kilograms? Beautiful. Okay? This is going to be my mass, right? If I wanted meters, I'd put like a distance or a radius or an x or something like this. Okay? So that's going to be in kilograms. Now, we just talked about this. What's the units for acceleration?
Meters per second squared.
Meters per
Second squared.
second squared. Okay? No variation on the thing. Okay? So let's say that I'm going to take this 1 kilogram mass, which I happen to have, right? And it's at rest. So if I want it to accelerate, what am I going to have to apply?
Force.
A force. So why do I have to apply a force to make it accelerate?
Because it has mass.
So
Nature wants to do the least amount of work.
Mother Nature is a lazy prima donna. Mother Nature says, I got a whole bunch of things to worry about, okay? If you want, basically, Mother Nature says, if you want the 1 kilogram mass to accelerate, you do it yourself. I'm not, okay? Now, if I drop it, hey, I'll let gravity do the work on it, okay? But right now, Mother Nature goes, it's at rest, I'm good with it. Mother Nature doesn't care at this point because she has other things to worry about, okay? So, I'm going to take this, I'm going to apply a force, and I'm going to make it accelerate, right? Okay, because without a force, guess what? It doesn't move, right? Okay, so I got a 1 kilogram mass, and let's say we get an acceleration of just what we did like with the car. Okay, let's say that that's 5 meters per second squared. Okay, that's kind of cool, right? So again, I get an answer of 5. Now at this point, you need to make a decision because there's 2 ways that you can write down the units. Okay, I don't care which one. It makes me no difference whatsoever. The old school, simple way to do this is to go, oh, I got kilograms times meters over seconds squared. Okay, I'm just going to keep everything there and go kilograms meters per second squared. So one way to express units of force is kilograms meters per second squared. It's cool, it's beautiful, it's elegant, it works. And sometimes you're going to want to do this, okay? But this is an option. Now at this point, physicists though are going, God, that's a god-awful amount of work. I got to write kilograms, meters, and then seconds squared and draw the line. I got better things to do. I've kind of got this whiny freshman voice, like, do we have to write all that out? No. So they said, okay, hey, who came up with the idea? Oh, Isaac Newton. Okay, right. Oh, he's kind of a cool guy, right? He had, if you ever see a picture, he had great hair. And he says, hey, let's call him Newtons. Oh, okay, right. But they didn't really want to write out Newtons either because that's even more work than writing kilograms meters per second squared. They said, oh, let's do this. Let's just put 5 with a capital N. Oh, that's so much easier. So this is the other way to express the units of newtons. You can either put a capital N or you can put kilograms meters per second squared. Those are your 2 options, okay? That's it. Now, with the newtons, make sure if you're going to go this route, make sure that you use a capital N and not a lowercase n. Because if you put 5 with a lowercase n, that's not the same thing. Lowercase n in physics represents a concept known as index of refraction. It has to do with how light gets bent going through different mediums, okay? So, if you're going to go this route, and that's fine, I don't care, but just make sure that it's an uppercase n. Or you can put kilograms meters per second squared. Which one you choose, I care not. Okay? Got that. Good. Great. All right. So, stop that for a second. Okay, so. Yeah, generally if I'm talking, the camera's on.
I thought so, but you didn't say anything.
I should have. I just, yeah. Okay, so yeah, it's like.
Okay.
When in doubt, turn it on. Okay. Yeah, because if I had gone like talk for the next 20 minutes, and then you would have said, did you want me to record that? Like, what? Okay. So, and this is on the back side of the lecture notes. You don't need to like write all this down. But usually in an experiment, you have 2 variables. You have an independent variable, and then you have the dependent variable. Okay? So you all have been probably taught this in 6th, 7th grade. So at the end of the day, what's the basic difference between the 2 of them?
Independent is not being changed.
What?
Not
No,
really.
it's what you.
Or is it?
Independent is
Oh,
what you
so,
change.
I'll
Dependent is what
test
changes
that.
due to the independent.
Okay.
Both of them change. You don't change both of them. Both of them end up changing.
Okay, so let's kind of work through an example, okay? So basically, the independent variable is the one that you can manipulate, okay? That's the one that you can control. And then your dependent, this is kind of a weird cyclical definition, but it works if you think about it. Your dependent variable is dependent upon changes to the independent variable, okay? Which sounds really, really weird until you think about it. So let's look at a simple example. So we're going to go out into the parking lot, and we're going to study the relationship between how fast a car is moving, its velocity, and the distance that it takes for the car to stop. Okay, that's the setup. So let's say that we're going to have the car going at 10 meters per second, okay, which is a decent clip, okay, right? You're not going to outrun a bullet with this, but 10 meters per second, decent clip, right? And you're going to hit the brakes, right? And let's say, and I'm going to measure that distance, and let's say that it took 2 meters, okay? Travel 10 meters per second, we hit the brakes, we measured it, and it took 2 meters, okay? Which is about like 2 long steps, okay? So a lot of times we're going to graph things. So what's going to go on the y-axis? Your independent variable or the dependent variable? On the y, okay,
I was like, yes.
Yes.
I was like,
I was thinking this and said y. Yeah, your y-axis is your dependent variable. Yeah, I've crossed myself up on that question. And this is going to be your independent variable. Now, don't write dependent, independent, don't write those down, okay? Everybody knows what they are. But here's what you do want to put down here. What do you want to put? A label. You want to label what it is and the units that go with it. So, here's the next question. Which one is my independent variable? Which one am I controlling? Am I controlling velocity or am I controlling stopping distance?
Velocity.
Velocity, because I'm determining how fast this car is going when I hit the brakes, okay? So my velocity is going to be my independent variable. So down here, I'm going to put velocity, and then I'm going to put meters per second so I know what that is. Because otherwise, I don't know. Is it miles per hour? Is it meters per second? What is it? Okay? So then my dependent variable is going to be my stopping distance, and that's going to be in meters. So here's the question. Mr. Shively, roughly, what is this graph going to look like? Here's 0, 0, okay? And let's say this is like 20 meters per second, and let's say, you know, sir, here's some distance of 10 meters.
Like halfway and pretty low.
Halfway and pretty low.
Like a straight line.
It sounds like halfway and pretty low. Okay. So like, is it going to start down here?
Yeah. No. Yeah.
No? Yeah.
Yeah.
It is? Yeah, because if I don't have any velocity, what's my stopping distance?
Oh, it'll start at 10 meters.
No, just, here's my point. You're making this way complicated, and
Yeah.
don't.
Yeah.
Okay? I'll tell you when to make things complicated. This is not the moment. Is the graph going to start at 0, 0?
Yeah.
Yes. And then what's it going to do from there? Do not make this complicated.
It's gonna go to the right.
Kind of like this?
Yeah.
Okay, there we go. International sign for a positive sloping line. Okay, or if you were in the 80s, that was like a disco move. Okay, which don't ever go back to a disco. Don't. I'm begging you. As you guys get older, death before disco. Okay, it was like polyester. It was bad. Okay, so not that rap is worse, but that's a whole other story. So you got some action like this going, right? So how did you know, Mr. Shifley, that this, logically, how did you know that this is, what's the graph?
It's just meters over time.
No. How do you know that the fact, why does this graph go like this? Because as the velocity gets bigger, what happens to your stopping distance?
It increases.
It increases, okay? It's a direct relationship, right? Okay, that's it. So this is why when you hit school zones, okay, what do they make you do?
Slow down.
Slow down. So if Timmy runs out into the road, right, you have time to stop in a reasonable distance before Timmy gets hit, okay? Just bang, right? Okay? You'll hear me, Timmy is like a staple of my instructional method. A lot of things happen to Timmy, okay? I use Timmy in chemistry, in physics, a lot of things happen to Timmy. I can explain all of thermodynamics with a second grade class full of Timmys. Okay. Gas crushers, the whole smash. Okay, so this is cool, but what if we said, well, I think the graph looks like this. So what would the blue line indicate?
Indirect relationship.
So that would mean the faster you go, The shorter the stopping, the shorter distance it takes to stop. So if the blue line was correct, and it's not, but if the blue line was correct, what would they make you do in school zones?
Speed up.
They make you speed up. Oh, school zone. Okay? Now, now, if you all have seen the carnage that happens with car wrecks after school when you all are trying to leave. With this line, imagine this was the line. Okay? Where the slower you go, the greater the distance. Imagine trying to park in mom and dad's garage. Oh, mom and dad have a pretty short garage. I get to get up to like 120 so I can stop inside the garage. Okay? Would be cool, don't get me wrong. But probably not.
Wouldn't you just die from stopping that quickly?
Okay, small detail. Hey, don't let reality get in the way of my story. Okay? Right? It's not right. That's the whole point. Okay? Yeah, you died. There's any. Yes. Gosh. That was the point. That was the humor in the story. Okay, we'll just strike that from the record. Okay. So. This is why physics teachers have like flat foreheads, because they go like this all the time. God, no. Okay. All right. So here's what you're going to do in the lab. Let me go ahead and hand out the lab. So stop that. I'll just hand out. Okay. So here's what you're going to do in the lab. And as far as like lab groups go, you all are big people, right? There's about 24 of you in here. I got 6, 7 lab stations set up. Okay. 3 or 4 people to the lab group. Okay. I don't want like 2 lab groups of 12. Okay? No. Okay? Like, we're working collaboratively. No, you're not. One person's doing the work and 11 of you are going, okay? So, here's what you can do. You can take a spring, and springs are cool, okay? And I realize that sounds horribly nerdy when I say this, but if you think about it, it's pretty cool. So, I'm going to take 1 kilogram mass, and I'm going to hook that onto it, right? And it stretches. Well, that isn't the cool part. But if you think about what happens on an atomic level, so what at its core level, what is that spring made of? Three things. Protons, electrons, and neutrons. I'll break those down farther to get into quarks, but that gets really weird. Now, here's the deal. If I take this off, what does it do? Goes back, right? Goes back. So it's like it has a memory, okay? So these electrons, protons, and neutrons get stretched. And they go, oh, right, this is bad, right? So then it says, okay, I'm going to go back to that original position. Now, if you do this with, like, say, for example, just like a piece of, say, Play-Doh. If I take a piece of Play-Doh up here and I stretch it out and let go of it, what's the Play-Doh going to do?
It'll stay stretched out.
It's not going to stay, yeah, it's going to stay stretched out. It's not going to go back to that original position. So something within that spring allows it to remember where it was. And when you take that off, it goes back to that point. And then even if I reverse it and like compress it, go like this and let go of it, it's going to go back to that point. So the spring has the ability to remember. So something happens in the arrangement of those electrons, protons, and neutrons that when you stretch it and apply that force to it, it goes, oh, this is bad, okay? And then it's going to go back because it remembers where it was. So you'll hear me use this analogy with penguin and in terms of memory, and you're going, what do penguins have to do with memory? This will make sense, especially as you get older. So the analogy is that your mind is like an iceberg, okay? And like you can only hold memories which are like representative of the penguins, okay? So your brain, your iceberg can only hold so many penguins. And so as you get older, the iceberg is full, right? And so like if you want to remember something new, a new penguin comes on, an old penguin has to get kicked off, okay? So it's like a Darwinian thing, okay? So these are the wire has like penguins. And so it's like, oh, okay, you're going to stretch it out, right? Okay, it's going to return back. It's not going to lose that memory, okay? The Play-Doh has no penguins because it doesn't remember what happened. But trust me, as you get older, the iceberg tends to shrink, okay? And then it holds like a fewer number of penguins. It's like, what'd you have for breakfast? I don't know. I kicked that penguin off. So it's like, Survivor, iceberg with a penguin. Like, I can only have so many penguins, and I'm not going to remember what I had for breakfast. Really not important. Okay, so this, trust me, as you all get older and you say, somebody will ask, hey, do you remember what happened, in whatever 5 years ago? It's like, that penguin sailed a long time ago. It's gone. Or some penguins won't even make the iceberg. I mean, it's just going to swing by. It's not even going to jump on the iceberg. Okay. Yeah, it's like I saw a freshman walk by today. It's like, oh, he's not me. No, I'm not even. No. Okay. All right. So we got an independent, dependent variable. So why does it take a force to stretch the spring?
Because it's at rest.
Nature's lazy.
Yeah, Mother Nature is lazy. Guess what? Because I could sit here and yell at it and go, stretch, come on, stretch, okay? And it's not going to, because Mother Nature is basically going, no, I'm good. I'm kind of chilled out right now, and you can yell all you want. I'm not going to move. But you say, okay, all right, I'm going to force you to do this. Okay, so I'm going to grab the spring, and then I'm going to apply a force to it. Now, I can use my hand to do this, but here's the problem. Hands are great. We have an opposable thumb. It's a cool deal, okay? One of the better inventions that we came up with. That and Oreo cookies. Opposable thumbs and Oreo cookies. Top shelf right there in my world. Okay, so I'm going to give this a stretch, and I'm going to pull it. That's cool. I can do this. Wow. But opposable thumbs are great, don't get me wrong, but they're not very good at quantifying the amount of force. Because if I grab this and I pull it down and say, well, how much force did it take? Some, I want to stretch it farther. How much force did that take? More. Okay? So we really can't graph like a little, some, and more quantitatively on a graph. Okay? You get an idea how much it took, but we can't really graph it. Okay, well, we need to come up with a way to measure an exact amount of force. So conveniently, this big rock that we're on, and this universe that we're in, we have gravity. Oh, that's kind of a cool thing, right? Because if we didn't have gravity, we wouldn't be here having this discussion, because you could have the Big Bang, and if there wasn't gravity, all the particles would just keep floating away from each other, and you would never form stars, and then you would never have anything going on, and we wouldn't be here having this discussion. But the million-dollar question is, why is there gravity in the universe? It's like, I don't know. It is. We're thankful for it. Just don't question it too much. So, this, all the protons, electrons, and neutrons in this, interact with all the protons, electrons, and neutrons on this big rock that we're on. Okay? And it creates a certain amount of force. Okay. So to calculate that amount of force between this and this rock that we're on, that's orbiting a very average star in a very average universe, a very average galaxy, we can mathematically calculate that number. So we're going to use the idea that F equals ma, because we're going to be talking about a force, right? So when I'm talking about a gravitational force, I'm going to use m, but instead of a, I'm going to use g, because when I drop that thing, it's going to cause an acceleration of 9.8 meters per second squared. So for the sake of this lab, and we're going to do this calculation a lot, to get that amount of force, because now I can exactly quantify how much force that is. And this is going to be on the front of the lab. I give you this example. So to get the force generated by that value, I'm going to take 1 kilogram, and I'm going to multiply that by 9.80 meters per second squared. Okay, 1 kilogram times 9.8 meters per second squared. Okay, right. I get 9.8. Now what units do I have? What are my two options? Newtons. And these aren't like fig Newtons, by the way. Isaac Newton had nothing to do with the invention of fig Newtons. Just pointing that out. Or I could use kilograms, meters per second squared. Which one you choose, I care not. Now, here's what you want to measure. Listen to me very carefully. What you want to measure is not the length of the spring. Okay, that is not what I want you to record. What I want you to record is how far it stretches from that equilibrium point. Okay? That's what I want. So there's a couple of things that you can do. The easiest is to measure this original length. What units are you going to use to measure this in? Meters. Probably you're going to have rulers. Probably you'll measure it in centimeters. Okay? But you're going to want to convert that into meters. So I know it's been a long summer. How many centimeters are there in a meter? 100. Okay? So it's like 12 centimeters. Are you going to divide by 100 or multiply by 100? Yeah, because if you're not sure, let's say it's 12 centimeters. Oh, 100 centimeters, that's 1 meter. Centimeters cancel out. I divide by 100. Okay, don't multiply by 100 and go, oh, how far did it stretch? 1,200 meters. That's like 1.2 kilometers. Okay, that's like a mile. Okay, bad. All right. So, what we're saying is that when I hook with this 1 kilogram mass, it's going to stretch 12 centimeters or whatever it is. So this is my data point. Here's my force, 9.8 newtons, and that's going to how far that's going to stretch in that equilibrium point. Now, what I'm going to do is I'm going to take a 1/2 kilogram mass. Now, this is 500 grams. Again, just to make sure everybody's on the same page. It says 500 grams. How many grams are there in a kilogram? 1,000, right? So if I got 500 grams, and sit here and go, oh, there's 1,000 grams in 1 kilogram. I divide by 1,000, I get a 1/2 kilogram, okay? So 500 grams, 1/2 kilogram, we're off to the races. So when I hook this up, let's do a little prediction. Do you think it's going to stretch farther, the same amount of distance, or not as far? Not as far. Why? Less force. Why is there less force? Why? Because there's less mass, right? Because there's less stuff in here to interact with the gravitational field of this rock that we're on. So since there's less stuff here to interact, there won't be as much of a pull. So I put this on, miracle of miracles, hey, it doesn't stretch as far. So now, the only thing that changes, I'm going to take 0.5 kilograms and multiply that by 9.8 meters per second squared. So if I take 0.5 times 9.8, I get 4.9 newtons or kilograms meters per second squared. So on the back side of the lab, you've got a data table. And I tell you exactly which masses to use. Now, the cool part about these masses is that you can like combine them, like I think one of them is like 800. So you can actually hook them together like kind of a chain of monkeys, right? They do this. Ooh, pretty, okay? You can use it as a Christmas decoration. We've got these cute little small ones, maybe an earring, I don't know. Really not my style, but that's just me. So, I know you find it shocking that I've never had my ears pierced. What?
So did you say that you only want to measure the distance from the original, like, so like the end of that spring right now, you'd only measure
How far it goes down?
how far it goes down?
Yes.
So then the initial would just be 0?
You speak words of truth. Okay? You're on a roll. You're 2 for 2. It's nice. Yeah. Okay. Now, so let's talk about the graph. So I got a stack of graph paper back there. And first off, what's your independent variable? What are you controlling? Elongation or force?
Force.
Force. Okay, because that's what we're going to change, right? So I'm going to have force here, measured in newtons. And then we're going to have my elongation here, measured in meters. Okay. Now, will the graph start in 0, 0?
Yeah.
Yes.
How much force is applied to this spring?
0.
0. How far has it stretched?
0.
0. This is why we do elongation and not length. Okay? So, and that's a key thing to look at a lot of times when you look at data. Ask yourself, will it start at 0, 0? Okay. So what do you think this graph is roughly going to do? As I apply more force, what do you think is going to
It's going to
happen?
be a positive.
Yeah, maybe something like this. Okay? That's what it should end up with. So what you're going to do is, here's the sequence. Today, make sure, you're going to go back and you're going to get your data. That's the first thing that you have to have happen. Okay, get your data. When you're collecting data and doing calculations, it sounds bad, but it is a universal truth. Always assume that your lab partners are idiots. Trust no calculation that they give. Trust no answer that they tell you. Okay? Trust me on this one. Always assume your lab partners are idiots. That doesn't mean like, hey, doorknob. That's not what I'm saying. I'm just saying be skeptical. This is the international sign for hey, doorknob. Okay, so just be skeptical, okay? Because here's what happens. Like, you all work together, and somebody will like enter something wrong into the calculator, like 0.5 times, 100, right? And you'll put it in wrong, and you'll get an answer of like 50,000, and everybody will blissfully write down 50,000. And then, unfortunately, when I grade it, I've got to go, really? All 4 of you did the same calculation by yourselves, and all of you got 50,000? Really? Okay, and then I have to get snarky, and it's just not, I really like that part of it, actually, I'm not gonna lie. Okay, so you're gonna have these data points. So actually, your first step, I'm gonna erase this. I love that. Okay, you're gonna plot your points. Now, odds are, these points are not all going to be exactly a linear fit. So you're going to draw a line of best fit. So what you're going to do is that you're going to take your ruler, you're going to start at 0, 0, and you're going to draw a line that's going to split these points. Then, and I give this very explicitly in the instructions, then you're going to come in here and you're going to circle points that you're going to use to find the slope of the line. Listen to me, you cannot use your actual data points to find the slope of the line unless they are actually on the line, okay? That's the whole point of this. This is what we're saying, this is the average slope. So what you find, what you're asked to find, and I tell you this, I'm going to look at this graph, I want you to circle the points, and I want you to write those x and y coordinates on this graph. And then you're going to find the slope. Now, refresh everybody's memory. How do you find the slope of a line? Change in y over, okay? So delta y over delta x. So here's what I'm going to look for. And you can either do it on the lab itself or you can do it on your graph paper. I want to see something minus something over something minus something. And put the units in here, okay? Put the units in here. When you find your slope, there's certain things I want to see. I want to see this, and don't tell me, I did it on my calculator. I don't care, okay? Again, I don't care about the answer if I don't see the process. Make sure that there's units when you get done, okay? Make sure that, because if you just have a slope and there's no units on it, it doesn't mean anything. The other thing, do not leave that slope as a fraction. Okay, there's three things that I really don't like. Freshmen, frizzies, and fractions. I'll start with FR. Coincidence? I think not. But, and I know the math people go, oh, leave it as a fraction. It's one. I don't care, okay? I want this thing as a decimal, okay? And we'll get into that tomorrow, like why it's important. This isn't just a Burkamp pickup, okay, or something like that. There's a reason that we use decimals, because it conveys how good our measurements are, that you don't get with a fraction, but you do get with the decimal. So you're going to have that. So here, and again, I'm going to say the R word. Read the lab. Okay? When I tell you this is how I want it done, guess what? That's how I want it done. Okay. There's a stack of graph paper back there. Okay? Everybody does their own. You got the questions, so this is due tomorrow. So go back, get the data, and then start answering all the questions. All right, go, fly. I'll print one out. Because I forgot that you were added to this class, and after I